Weather marker, inbound for auto landing. Roger, Foxtrot Papa. You are clear to land. Surface wind is 230 degrees, 10 knots.
You have just seen a fully automatic landing by a research aircraft operated by the flying unit of Smiths Aviation Division. This aircraft is equipped with Smiths SEP5 flight control system. And the evolution of this multiplex system is the latest stage in a development program started in 1948, when Smiths began collaboration with the blind landing experimental unit of the Royal Aircraft Establishment. The single-channel auto-land system that resulted from this partnership started practical trials several years ago, and aircraft using this system have already made many more automatic landings than all other known systems combined. A single-channel military system similar to Smith's SEP4 autopilot has been adopted by Britain's RAF and is being fitted to aircraft of the V-bomber squadrons. In the course of its development, single-channel or multiplex automatic landing equipment has been installed or is being specified for many different types of new generation civil and military aircraft, both propeller-driven and jet. These aircraft also include the Canberra, the Argosy, the Comet, the DC-7, the Transal, the Varsity, the Caravelle, the Belfast, and the Trident. The complex mechanisms and instruments required for these installations are made by Smiths at their Cheltenham factory, the first to put such equipment into full production for operational use. Careful precautions must be taken in manufacturing this kind of equipment to exclude dust and dirt. For example, the miniature and sub-miniature rate gyros that have been developed for the latest generation of autopilots are assembled and tested in a completely sealed assembly shop under strictly controlled and ultra-clean conditions. Even individual ball bearings are microscopically examined, and before the hermetically sealed gyros are allowed to leave the assembly shop, they're subjected to searching tests. For each of these very small instruments is required to do its work for up to 4,000 hours without an overhaul. While the single-channel or simplex autoland system provides a standard of reliability and touchdown accuracy appropriate to military aircraft, a higher level of safety is required for civil operations. In fact, the possibility of an accident must be no greater than 1 in 10 million landings. This requirement could not be met with the simplex system, which has no built-in monitor. A single fault can cause an unwanted maneuver, and at low level, the pilot might not have enough time to restore the aircraft to the correct flight path. It is for this reason that Smiths have, since 1957, been working on the development of the SEP5 flight control system, which utilizes the multiplex principle. One example of this is the duplex system, which consists of 2 independent sub-channels in each axis of control, working together and continuously checking on each other. Any failure in either will result in the disengagement of both, and thus cause no appreciable disturbance to the flight path. The pilot can then take over control of the aircraft and either land or go round again. For regular automatic landing under blind conditions, however, even this level of safety may still be inadequate, and 3 or more independent subchannels are required to meet this stringent operational requirement. The failure of any one of them will now result merely in the disengagement of that subchannel alone, leaving the others to complete the landing. The SEP5 multiplex installation in the de Havilland Trident will be used initially as a duplex system and subsequently at triplex or 3-channel level. Although the Trident will not initially make fully blind landings, its duplex system is designed to be capable of auto flare or auto landing in comparatively good weather as a necessary preliminary stage. For auto flare, lateral control in the final phase of landing is taken over by the pilot, while pitch control of the aircraft remains automatic throughout. The duplex pitch channel system brings the aircraft down the correct glide path to a height of about 150 feet. When the glide path coupling is disconnected and the aircraft is locked at a pre-computed pitch attitude. This attitude phase is maintained to about 50 feet, when the radio altimeters take control through the autopilot and complete the flare phase automatically. Azimuth control of the aircraft is automatic down to about 150 feet, which is the point at which the pilot takes over. He controls the aircraft laterally during the automatic flare maneuver and kicks off drift. This auto flare concept is based on the established fact that a pilot emerging from cloud has better visual guidance in azimuth than in pitch. When sufficient experience has been gained with auto flare, the Trident system can be used for full automatic landing at duplex level, or extended to triplex level to provide regular blind landing. In the Trident cockpit, every effort has been made to achieve a clean and uncomplicated layout of controls and instruments, and the same principles have been applied to the housing of equipment in the forward equipment bay. Here, all the drive amplifiers and computers are carried compactly on Smiths ATR racking, with space provided for the addition of further units when the system is operated at triplex level. A third independent power supply is also available in readiness for this development. Modular design and the use of Smiths ATR boxes ensures that all units can be checked, serviced, or if necessary, changed very easily and quickly. The junction box is located at the back of these racks, while the radio junction box is at the side. This incorporates 3 Smiths radio switching units, which enable port and starboard VOR and ILS information and Doppler information to be fed to the autopilot and flight system. The vertical reference units and azimuth gyros are also conveniently arranged and easily accessible. It is the triplex version of the SEP5 system that has been installed by Smiths in this specially converted research aircraft, which has been allocated to them by the Ministry of Aviation as part of the development program, and is the first aircraft in the world to be fitted with an automatic landing system at triplex level. One of its important functions is to enable pilots to gain experience in the system by using it in genuine fog operations, as distinct from simulated conditions. In addition to automatic landing, the SEP5 system provides many new flight director and autopilot control facilities, and these will now be shown in the course of a typical flight. Just before takeoff, the pilot switches on the flight director master and sets initial climb reference. The aircraft leaves the ground with all power supplies turned on, gyros and flight instruments working, but with no controls engaged. While gaining height, the pilot flies the aircraft manually, using the full range of flight instruments. At a few hundred feet, he selects the autopilot by using the engagement levers. This brings in automatic control to hold the aircraft at constant attitude. He now engages the airspeed lock and selects the required climbing speed, then sets his heading on the port flight compass and moves the radio coupling switch to the across position. When the azimuth master is switched on, commands from the steering index are made available to the autopilot and the flight director. The aircraft now turns to the heading shown on the steering index. We're now cleared to cruising altitude, and the pilot uses the two-position setting knob on the flight controller. First, to set the prevailing pressure on the millibar counter, and then to operate the select height counter. He switches the height lock selector to acquire and pulls on the engage switch. For radio navigation, the system includes two radio selectors which enable the pilot to select the radio information to be displayed on each flight compass. Before coupling to VOR, he switches the port radio selector to nav1, and the co-pilot switches the starboard selector to nav2. He then tunes number 2 radio to the VOR station and sets the starboard flight compass to the desired radial. This causes the VOR2 information to be shown by the flight compass roller blind display. He then moves the radio coupling switch to the up position, thereby coupling the flight control system to the VOR information. The port starboard switch enables the appropriate azimuth commands to be fed into the autopilot. The aircraft subsides onto the VOR radial, and the Doppler drift maintains the precise track. We are now approaching our cleared altitude, and the height selector switch drops back to the lock position as the aircraft intercepts and holds flight level 90. Although we're not flying fast enough to see it working, the system also provides a Mach lock facility for use in faster aircraft. The VOR station is now almost below us, and when the aircraft enters the cone of confusion, the radio signal is suppressed by an automatic sensor in the azimuth computer and reconnected on leaving when the flight compass roller blind display changes to VOR from presentation. We're nearing our destination now, and the pilot selects the required rate of descent on the flight controller, pulls on the engage switch, sets the prevailing ground pressure and the selected height, switches the height lock selectors to acquire, and pulls on the engage switch. At this point, we revert to steering index control. The pilot sets the radio coupling switch to across and takes azimuth control by moving the port starboard switch to port. Numbers 1, 2, and 3 navigation receivers are tuned to the airfield localizer, and this causes the flight compasses to display ILS information. The runway QDM is now set on both the starboard and port flight compasses. The pilot slows down the aircraft, sets the speed lock selector on the flight controller to throttle, pulls the engage switch, and uses the setting wheel to select the required initial speed. The acquire height switch on the flight controller now drops back to the lock position. And a moment or two later, the aircraft intercepts the selected height. At this stage, we're flying a heading under radar control. But now, the radio coupling switch is moved to the up position, thereby coupling the flight control system to the ILS beam. This fact is shown by the beam indicator on the flight controller. As the aircraft intercepts the localizer, the blue and yellow areas on the flight compass display begin to move. We're now flying inbound on localizer. For the sake of brevity, we've made a radar-assisted interception of the beam. But the system has flexibility for covering all intermediate procedures and holding patterns under full automatic control. In the auto-landing sequence which follows, the pilot's hands will be off the controls in order to demonstrate autopilot performance. In actual operations, he would normally monitor the controls and the cutout button, in addition to the full range of flight instruments and warnings. He now sets the prime switch to glide. And when the glide path deviation pointer on the flight compass becomes central, the nose of the aircraft automatically goes down as we couple to the glide path. At the outer marker, the pilot checks the height and sets the initial speed for the approach. Meanwhile, the flight systems panel has been checked to see that the autopilot is clear for a landing, and the radio altimeter confidence switch is used to check the 3 landing indicators for readout. The pilot now sets the prime switch to land. The altimeters are now indicating actual height above the ground. An automatic overshoot can be initiated at any time on the approach down to flare by pushing the throttles fully forward. This will lock the autopilot to approach speed reference for climb out. The autopilot can, if necessary, be disengaged by its cutout button or by force disconnect. At about 100 feet, the radio altimeter signals disconnect glide path coupling, and the aircraft continues at constant attitude. At 50 feet, the aircraft starts to flare under the control of the radio altimeters. And the last phase before touchdown is the land phase, in which the effects of any significant crosswind are cancelled out by rudder action. Comprehensive safety provisions are embodied in the SEP5 system, which is standard equipment in all BEA Tridents. Warning flags are provided in the altimeter, attitude director, and other principal flight instruments which signal any malfunction. The centralized warning system alerts the pilot to any failure of a key service in the aircraft. Other safety provisions include the flight systems panel, which, as we've seen, indicates the state of engagement of the automatic controls. In the Trident, with its present duplex installation, the automatic system will disconnect after a failure, opening the shutters of the PVD displays, which give instrumental guidance for reversionary control. As the PVD displays are controlled independently of the autopilot channels, the safety of the system is of a very high order. The Trident enters service as the world's foremost civil aircraft in the sophistication, versatility, and safety of its flight control facilities, and as forerunner of the not far distant day when all-weather operation and automatic landing will be an everyday part of airline service.